Hi, and welcome. So in this video, we'll be talking about future value of ordinary simple annuities. I'll show you a basic example of future value for ordinary simple annuities and explain to you on how we arrive at the annuity formula, right? So with that being said, let's quickly get started. So here we have a question that shows that Elizabeth invests $1,200 at the end of each year in a savings account for 3 years at an interest rate of 5% compounded annually. What will be the total value of your investment at the end of 3 years? So again, with any time value of money question, the first thing we have to do is draw out the timeline, right? So when we draw out the timeline, we see that she's making a payment, or in this case, investment, sorry, at $1,200 at the end of each year, starting in year 0. So the end of year 0 and beginning of year 1, she's made $1,200 of the installment, right? In year 2, she's done that again. In year 3, she's going to do that again. So what we need to find is just the future value of each of this $1,200 to see the total value of our investment, right? So what we can do is we can actually use the compounding interest formula for future value to find this, right? Now, another thing we have to keep in mind is that this time period is compounded at 5% annually. So we're just going to use our future value equation to solve for each individual $1,200 and see what it's worth. So let's quickly get into that, right? So we're going to start in year 3, and that's why our n is equal to 0 in year 3. That's what it is. And if we go back 1 year, we're going to calculate n equals 1. So we're going to calculate the $1,200 worth. What would the value of the $1,200 be if we go back 1 additional period, right? So your n there, in that case, is going to be n equals 1. And if we go back one another time, so that's 2 years from year 3, your n is going to equal to 2, and you're going to get $1,200 multiplied by the 1 plus I to the power of n, which is 2. And this is the total value in each case. In the first case, you get 1,200 because anything to the power of 0 is 1. 1 plus 5 to the power of 1 multiplied by 1,200 is going to give you 1,260. And to the power of 2, 1 plus 5 multiplied by 1,200 is going to give you 1,323. Now, if we sum this up, we get a total value, which is going to be the value of Elizabeth's investment at the end of 3 years. We get it as $3,783. Now, we see something common in this, right? You know, we got a 1,200, which is like our start term. We got a common ratio. You know, this looks a lot like a geometric series, right? Where you, again, in a geometric series, you have A, which is your start term, and your R, which is your common ratio. You multiply, then you multiply R, which you get R squared, and so on and so forth until you get to your last term, which is your start term multiplied by your common ratio to the power of n minus 1. So this equation is the same as this, right? Now, we don't want to use this because assume if Elizabeth had 15 years of investment for $1,200, there's no way we're going to go ahead and calculate the power of 15 for all that 15 future value formula questions, right? Like, we're not going to do that. We're not going to compute it. That's going to take forever. So what we want to do is we want to see if we can simplify the S sub n, the sum of the total, all the investment, and see if we can arrive with a formula, right? So to do that, a generic formula to do that, what we can do is, just look at the formula, and we see something common here, right? It's the R, which is your common ratio, right? Which is it's common, right? It's there in every there. It's there, right? So what we can do is just multiply this whole equation by R and see what we get. If we multiply this equation by R, we get R multiplied by S sub n is equal to AR, because now your A, which was R to the power of 0, has become AR squared, because it's multiplied by R to the power of 1, and so on and so forth. Now, we have two equations, right? So what we can do here is that we can use the elimination method to subtract the common terms in each equation, right? So we can subtract the common terms in each equation, so such as AR squared, AR cubed, all the way up until AR to the power of n minus 1, right? We can take it from AR all the way to AR n negative 1. So if we do that, we can just cross those out, and we're left with just these 4 variables. And if we just simplify that and write what we're left with, we get S sub n minus R, which is your common ratio multiplied by your S sub n, is equal to your start term multiplied start term minus start term multiplied by your common ratio to the power of n. That's what you're left with. So what we can do this, we can take this even a step farther, and we can factor this and simplify it, right? Because we see some common terms here. So what we can do is just factor it and simplify it, right? So the common term on your left side of the equation is S sub n. So if we factor that out, we're left with 1 minus R. And similarly, on the right side, if we factor out A, which is your start term, which is the common here, if we factor that out, we're left with A multiplied by 1 minus your ratio to the power of n. And now what we can do is just simply divide each side by 1 minus R so that we have an equation to work with. So if we do that, we get this equation, right? S sub n into your first term multiplied by 1 minus your common ratio to the power of n divided by 1 minus your common ratio, right? Now, with that being said, this is an algebraic formula, right? So you can subtract one from the other. Now you can, with that being said, you can actually take the second equation and subtract it from the first equation. So that would be also correct. So if I were to do that, I have that on this side. I've just taken the second equation on this side, and I've subtracted by I just reversed the order, and I'm just subtracting the bottom equation by the top equation, right? So if I do that, I'm left with R sub n, R multiplied by R sub n, minus S sub n is equal to A, which is your start term, multiplied that by common ratio to the power of n, and subtract your common ratio from that. My bad, subtract your start term from that. And once we do that, we have a factor, and we simplify, right? So we have, and then once again, on the right-hand side, all you have to do is sub out, factor out the S sub n, and you're left with R minus 1. And on the right side, you're just factoring out your start term, so you're left with R to the power of n minus 1. Now, the only difference between these two equations is that they're both right. You can use them both, but it's important to identify when to use them. So, so now that you're out of both equations, so when you use this equation is mainly used when your R is less than 1, right? When your R is less than 1, that's when you use this equation. When your R is greater than 1, in that scenario, you'd use this equation. And in our case, in Elizabeth's case, her R is greater than 1, right? The compound, like, she's investing at 5% compounded annually, so the R in her situation is greater than 1, right? So we're going to use this equation. Now, let's go ahead and see if we can figure out the variables here and see if we can use these numbers given here, whatever the given numbers are, and see if we can use this equation to solve it. So let's do that. So here we have Elizabeth who invests the $1,200, right? It's the same question again, and we have our timeline. It's showing the same thing. Year 0, year 1, year 2, she's making that investment, right? So what we want to solve for is the S sub n. But what we need to know is which formula to use. And we're going to use the formula in which your R is greater than 1. And that formula is S sub n is equal to your first term multiplied by R to the power of n minus 1 divided by r minus 1. So your s of n is unknown because obviously we don't know that. We're trying to solve for that, and that's why we came up with the equation. The next thing is we need to see if we know what a is, which is our first term. And our first term, we can state that is $1,200 because that's what she's starting off at. So we know that a is equal to 1,200. Now, do we know what r is? Yes, we also know what r is because r is equal to 1 plus I. In this case, I is 5%, so it's going to be 1.05. That's your r. And lastly, n is given as 3. So there you go. You have your n as 3. Now you have all your variables and you've identified them. Now all you need to do is just simply plug it into the equation and arrive at your answer. So that's what I've done here. And obviously you'd use BEDMAS. So the first thing you do is just factor and solve for this, right? So if we solve for 1 plus 5 to the power of 3 minus 1, we get 0.157625. And we multiply that by $1,200, and we'll get 189.15. And then we just divide that by 5%. And look, it's the same value, $3,783. So this geometric equation works. It helps us identify or solve what the total value of Elizabeth's investment would be. So now what I want to point out is that this is a geometric equation, right? And we're dealing with annuities. Now, why don't we make it a little simpler where we can identify each of these variables with the annuity formula, right? Or the annuities, whatever is happening in that, right? So, like perhaps we're looking for future value, but anywhere here, we don't know what the future value is. We're using it as S sub n. We're seeing that as that. So what we can do is just simply rearrange the formula so that your variables look similar and more understandable for you to grasp the future value of ordinary annuities. So to do that, all I have done, or the equation, what we're supposed to do, is just substitute similar aspects of it, right? So S sub n, you're looking for the total value. In this case, your S sub n is going to be a future value, right? Because again, your future value is at the end of the term, you're trying to look for the total value of your investment. So that's what you're going to use. Now your A, which is a start term and which is a constant, you can note that as 1,200, and it's going to be your payment. It's happening over and over again for the next 3 years. So we can write that as PMT. As per your R, you could simplify it by writing 1 plus I to the power of n. And exactly at the bottom you write 1 plus I minus 1. The 1 plus and the negative 1 crosses out and you're left with just I. So there you go. You have this equation for annuity. And let's see if this equation works for you to solve the question. So again, FV, we don't know what that is. PMT, yeah, we do know what that is. She's making an equal payment of $1,200 at the end of each year for 3 years. So we know that. We know the interest rate, it's 5%. That's stated as here, 5% compounded annually. Lastly, we know the term, it's 3 years. So we can use that as well. Now, all we need to do is just simply plug it into the equation and see what we get. So the first step was to simplify this, 1 plus 5 to the power of 3 minus 1. And when we do that, we get 0.157625. We divide that by 5%, so we get 3.1525. And we multiply that by 1,200. Can you guess what the answer is going to be? You're right. It's going to be $3,783. So it's the exact same amount we've calculated. So we now understand that the geometric series or the geometric formula that we've arrived at is used for annuities, and we can use that to solve any annuity question. So this was a very basic question. I hope this video helped you. If it did, please give it a thumbs up, like, and subscribe to my channel. If you have any questions, please comment down below. Thank you.